So we have a, uh, the possible column spaces inside R3. So let us say the linear combinations be A1 x1 plus A2 x2 plus A3 x3, and this corresponds to the entire R3. Yeah, of course, A1, A2, and A3 are the um, independent independent vectors. So if I take any two of this, it gives me it gives me a plane. It gives me a plane. If I take any one of this, it gives me a or a line. Let us say it's a space, it's a plane, it's a line. So here A1 is not equal to 0, A2 is not equal to 0, A3 sorry, is not equal to 0. Here in this case A1 is equal to 0, A2 is not equal to 0, A3 is not equal to 0. Here A3 is not equal to 0, A1 is equal to A2 is equal to 0. So there could also be a case where A1 is equal to A2 is equal to A3 is equal to 0. So that would be the 0 vector. So that is the point origin. This one. Okay. So we were talking about a matrix in the last class. No. Let us say talk about this. 110321. So this is A. If this is A, what is C? Or let me ask you, you tell me the um, what is the column space of A? What is the column space of A? Here, as you can see, 110 and 321. These are the two independent vectors. Now let us talk about 431, the third vector. whether that is independent or not. What is 431?
So it is dependent on the first two vectors. It's a sum of the first two vectors.
That's right. So column 3 is the sum of column 3 is equal to column 1 plus column 2. Hence, uh, the third column is dependent. So even though it's it has got three vectors of in the 3 dimension, it's still the column space, it's still a plane. But the question is, how do I get, how do I know the independent columns? The very simple technique is, the very simple technique is take A, take the matrix A and start preparing the columns. So let us take the first matrix, I'm sorry, the columns. Take the first vector, first column, and see to it that it is, I mean, not all of them are zeros. If not all of them are zeros, let us put them in the independent columns. Okay. The second step is to take the second column and compare it with the first column and check whether the second column is a multiple of the first column or not. If they are not, then simply put it here. Take the third column 431 and check it with the first two columns whether it's a combination of the first two or not. Here in this case, column 3 431 is a combination of first two. So 3 1 2, I mean 3 plus 1 2 plus 1 1 plus 0. So hence it is not, and there is no more columns left. So stop it here. So in this way, the column space is 1 1 0 3 2 1. So if I take another matrix, let us say A is equal to 1 1 0, 2 3 1, and then um, let us say plus 1 3 5 7. So if this is A, what is C? Non-zero. So the first one. Let us talk about the second one. 2 3 1. Is it a combination? Is it a multiple of 1 1 0? 2 3 1. Is there any scalar quantity with which if I multiply 1 1 0 that it becomes 2 3 1? The answer is no. So I'll put 2 3 1. So 3 5 7. Take any combination of the first two columns 2 1 3 1 0 1. Is there any such combination available? 2 plus 1 is 3, 3 plus 1. No, I don't think there is any such combination available. So 3, 5, 7. So the number of columns are also same. I'll take another matrix. What is the column matrix? First one is 1, 1, 0. That's true. The second column 3, 3, 0 is a multiple of the first one 3 times. So I cannot take that. What about the third column? Third column is also a multiple. So I cannot take that. So with this, we have the column dimension here in this case. The column dimension is 3. There are 3 different columns are there. But then the rank, there comes a new word called rank, is equal to 1. Here rank, we denote it with R, is equal to 3. Here rank is equal to 2. Even if n is equal to 3, n is equal to 3, and n is equal to 3. Given n equal to 3, and here is the matrix dimension, 3 cross 3 here I am writing. So given n equal to 3, the rank here in this case it becomes 2 for this matrix. For this matrix, this becomes 2. For this matrix, this becomes rank is equal to 3. This matrix rank is equal to 1. So what is rank actually? What is the rank?
Number of independent rows or columns.
That's number of independent columns. Okay. Now here I forgot to mention one more term known as basis. Basis. This is an important term. I Let me go here to the starting of this class, today's class. So here the linear combination of A1, A2, A3 with x1, x2, x3 forms a space. When one of the vectors A1 is dropped here, it forms a subspace of the total space. R2 is a subspace of R3. Similarly, R is also a subspace of R3. Similarly, the 0 vector is also a subspace of R3. So, what is the basis for these subspace? The independent, the set of independent vectors are known as the basis. The set of independent vectors forms a subspace. And basis defines that subspace. Okay, so coming back to this rank, coming back to this rank, rank uh, is the number of columns. Now, when I say number of columns, obviously there has to be another word called rows. Obviously, there has to be another word called rows. Now, what is that row actually? What is that row? So let us take the first matrix. We have the first matrix as 1 1 0 3 2 1 4 3 1 1 1 0 3 2 1 4 3 1. This is equal to 1 1 0 3 2 1 1 1 0 0 1 1. Can I write it in this way? A is equal to 1 1 0 3 2 1 4 3 1. Here I am writing the number of columns, that is the C matrix. Here I am writing another matrix, that is R matrix, or so to say A is equal to C times R. And I am writing A is equal to C times R, and obviously they conforms with the matrix multiplication. 3 cross 2, 2 cross 3, answer is 3 cross 3, they conform. And from here, what do I understand? It's actually I have factorized the matrix A into two different matrices. One is the column matrix C, another I am telling it as a R, or the R for rows, or in fact. So uh, look at the first 2 cross 2, first 2 cross 2. They are actually, the pattern is fixed, whereas the third matrix that defines, the third vector that defines what is actually the combination of first two vector. Okay, so here when this first vector, or the first column, um, yeah, the first column multiplies with the first column of this R, and Yeah, sorry, some disturbances are there a little bit. Just a second, I'll be back. Well, let's resume. So A is been factorized into two matrices C and R when the column matrix C multiplies with the first row, sorry, the first column of R, 1 and 0. So this is nothing but 1, 1, 0, 3, 2, 1. It multiplies with the first. Oh, what is the answer? Answer is 1, 1, 0. That's right. Similarly, when it is multiplied with the second, the answer is 3, 2, 1. And the third one, 1, 1, 0, 3, 2, 1. That is actually give the sum. So in total, we are getting the same matrix only. That's right. Now, in the other way, for each set of columns, there is also each set of rows are also there. So rank is nothing but number of independent columns. I can also write it is an independent set of rows also. Now, does this matrix factorization, I mean, do they uh, explain you something? These two, do they explain you something? Why at all? Regarding C, we have understood. So why at all R should have independent rows? And the answer lies with this. Answer lies with this. This actually corresponds to the first two columns of the C, and the third one is nothing but a combination of the first two. And that is what this R actually represents. Well, there are some disturbances here. Can we stop the class today? We'll continue in the next class. Okay. Thank you all.
Thank you, sir.